Any question to ask from last week lecture in Victoria? Still downloading my lecture notes. Okay with the content, the solution I gave last week. Next week we'll have a quiz, but the quiz may be a little bit harder than the previous quiz. Maybe more work have to be done. So be prepared. Still downloading the quiz, the lecture notes. In the meantime, so in your exam, right? If you ask to show, you should explain every step you use, right? So instead of just writing the left-hand side here, you should explain what you did. Okay. Explain what you did on the right-hand side. What? What? Shop. No, wait. Because this is actually automatic, right? So why you write this step? There should be a reason why you write the step, right? I'm not asking you to write a sentence there because of just say by what? By definition or by some law, the Morgan's law, by definition. That's all. You don't need no need to like write a whole paragraph. I think I did this in the lecture notes, right? In the tutorial, I asked you to find the law I use. Yeah. Okay, thank you. Thank you for the support. So yeah. Yeah, you don't need to write a whole sentence, but just write few words to explain what you did is enough. Okay. Don't just write like this. Explain what you do. They should come like automatically, right? Because if you know why you write this, then you should know what's the review. Yeah, today we will talk about function and matrix. I upload my lecture notes to online. I need to download it. So the line is very slow. Half an hour already. That should make a big file. Maybe I just let me see if I got some. Let's see, I've got some extra copy. Okay, maybe I open up the textbook and then we start from there later after my download. Hmm. Okay, maybe we just start. Let's see what I remember. Okay, so let's start with functions. So what we have studied, so we studied propositional logic. Okay, so we know how to write sentence statement that's true or false that can be determined true or false. And then we learn set theory, how to put items together, um, how to study a collection of objects. Now we want to establish bridge between sets. Okay, establish bridge between sets, between elements. Okay, so in that case, then we need to start with two uh, non-empty sets. Okay. Okay. So for every, so what is a function? A function is an assignment, okay, such that is an assignment such that for every A in A, okay, so for every element in A, in the set A, we assign a unique uh, B so that F A equal to B for some B in B. Okay. So for every A, we assign unique B. So okay. So sometimes we call functions is called uh, mapping, okay, or transformation. Okay, it's called mapping or transformation. And okay, so for every A, we have to have a B. So usually A is called Then A is called a domain. Okay. B is called domain. Okay. Uh, so everything in the domain will be get mapped by F, but F not necessarily will map to every element in B. Right. So for example, you can see this one. So let's say we got three element in A, and then four element in B. Right. Okay, finally done. So we could have like the map like this maybe. Okay. So the things that we map to will be in the range, will be called the range. So the range is FA, which has the element such that y equals to FA for some A. Okay. So in other words, FA is a subset of B. Right? Remember we learned subset last week. Okay. Okay, good. Yeah, okay. So finally, this is range, this is domain, this is codomain. Okay, then the middle one is a F. Okay, so range of F, or sometimes we go the image of F. You can see on image. Okay, image of F. Okay, okay. Also, if y equals to, yeah, use one method. Use y equals to fa. So if y in B, okay, and y equals to fa for some A, then A is the pre-image of B, of one. Okay, so we have pre-image, range, image, domain, and codomain. So domain, codomain is a set, and then range is also a set. Okay, image could be image of a set or image of a, okay, let me rewrite this. So this one should be called the image of A, and we also can have image of a element. Y is the image of A. Okay. Okay. So anything get mapped to the image, and then the thing that gets sent to the thing gets sent to the image is called a pre-image. So pre-image live in here. Pre-image of some element live in here. Okay. And then image live in here. So some few words you need to know is domain. So okay, maybe I list it up. So you got the domain, right? And then you got codomain. Okay, and then you got the range here. Okay, and then you got F that connects the two. You got pre-image living in the domain, and then image living inside the image. Okay, this is a set inclusion between the okay. Okay, for example, what kind of function you have? You have function from real to real, okay, where you can consider sending x to x squared, or you also can consider function also going from R to R, but send x to x cubed. Okay, so this is fx equal to x squared, and then gx equal to x cubed. So given me an x, I squared it and then I give back to you. Give me an x, I cube it and then I give back to you. Okay. So this is the domain. This is the codomain. Okay. So for example, let's see how to read this word. So word is the image of 2 under f. What's the image of 2 under f? Oh yes. Okay. So 2 is the pre-image of 4. Okay. Okay. So next, okay. Next function. So okay. So next. So next, a function is called real value. If its codomain is the real number. Okay. Maybe I just say it's real. Okay. And then integer value it is z. Okay. So depend on where the function lands. So we'll call it real value or integer value. Okay. And then the next thing is this function also have some algebra structure. So you can given two real given two real value functions, for them fg. Okay. So they have the algebra structure, so they have two operations. So you can either add them or multiply them. Okay. So first you need to think how to define them, right? So how to define them? So you give me a number. So let me set their domain and codomain first. So from A. So give me an element in A. You need to tell me like uh, how they send element to R, right? So can you guess how I define the function? How to send an element in X to what? Hmm? So for the sum, any idea? How should you define this element here? Fx plus gx. Okay. Similarly, you can define fgx by fx times gx. Okay. So this is the algebra you have on the function space. So these are well defined, first of all, right? Because given two real value function, okay, so we know where f sends x going to, right? And also we also know that g will send x to some well defined. G is well defined, then g will send x to somewhere else, and then they both lies in R. Okay, so you can add number in R. Similarly, you also can multiply number in R. Okay. So for example, so just now we got the two function, right? Remember, fx equal to x squared, and then gx equal to s cubed. Okay. So what is f plus gx? Is what? S squared plus s cubed. Okay. How about fgx? Yeah, x squared times x cubed. X squared plus 5. Okay. Yeah. Maybe it looks like very uh, trivial. I don't say easy, but trivial. But this is like this is concerning how you define a function. Okay. How we understand this definition of function. Okay. It is trivial, but make sure you understand the definition. Why we can do this? Okay, because each of them are defined for, and then the addition here is the addition of real numbers. Okay. Okay, next. So yeah, I think I made this before. Mhm. Okay, then we have two key property that a function will hold. So first is one to one. Okay. So a function is one to one, or we call it injection. Inject if and init, if and only if f a equals to f b implies that a equals to b for all a and b in okay, let me set the domain space. Let's call domain space. Maybe use x and y then. Yeah. So a and b. Okay. Were you confused or not? Maybe I use a1, a2. I say a1 to a2. So all a1, a2 in a. Yeah. So you check the two things is equal here, then it must come from an equal element here. Okay, this is what it means. But I will show you how to check. Then f is oh no, f is injected. Okay. So note that this one is a P implies Q, right? Yeah, so logically equivalence, if this is not true, then this is not true. So to check uh one-to-one, there are two ways to check. One way is to assume FA1 equals to FA2 implies A1 equals to A2, or you start with A1 not equals to A2, and then you show that FA1 is not FA2. Okay. So let's see an example. So let me jot down what I said just now. Similarly, if A1 not equal to A2, then A1 not equal to A2. Uh-huh. So fx equal to s squared is not uh, injective. Yeah. Why is it not injective? Any idea? Huh? And then what? Huh? No, no, no. So if you want to show it is injective, right, you need to show that mm, if this is true, but this is a false, right? So any question or not? I see confused face, confusing face. Uh, okay, maybe draw picture is easier. Okay, okay, draw picture. So so injective, you want one to one. One to one is like to one to one. Okay. If you have a map like this, then this is two to one. So it's not injective. It's not one to one. Okay. So why is it fx equal to s squared is not injective? Huh? Why is it fx equal to s squared is not one to one? Huh? So we can take uh, x equals can take 1 and minus 1. Right. Yeah. But f1 equals to 1. F minus 1 also equal to 1. Right. So they are not equal, but they are after the mapping is the same. So it's not injective. Okay. Uh, but gx is injective. Yeah. Right. So you need to start from here and then prove here, right? So suppose GA1 equals to GA2, right? Then A1 cube equal to A2 cube. Okay. So how to show A1 equal to A2? How to show A1 cube equal to A2 cube? Anyone got any idea? A1 cube equals to A2. No idea. I also don't know. Maybe I think okay. So far I don't. I think I don't know. But we can use another method later. So this one maybe keep it later. Use another method. Okay. Unless you know the number theory. Okay, which is this one. Okay, maybe need to use this method here. Okay, so after we learn this one-to-one, okay, now we want to introduce increasing. Okay, so let me say what is increasing. So let the function from um, A to B such that A and B are subset of R. Yeah. So I use all the notation we learned last time, and we say that f is increasing if fx less than or equal to fy. Okay, and then we said that fx is strictly increasing. And, for level of something, this doesn't make sense. Okay, hey, when you see this kind of sentence, right? This kind doesn't make sense because I didn't tell you what is x and y. So I should say for x less than y. Okay, and then strictly increasing if fx is strictly less than fy, also for x less than y. Okay, and then it's called maybe I just repeat f is decreasing if fx is uh, greater or equal to fy for x less than y. Okay, and then f is strictly decreasing if fx is greater than fy for x less than y. Okay, we can't just now we can't show that fg is one-to-one, but we can show that g is strictly increasing. So gx equal s cubed is strictly increasing. Okay. So how to prove it? So we want to prove. Actually, we prove by cases. Proof by cases is easier. We split this graph into 0 to positive infinity and 0 to negative infinity. So suppose your point is greater than x. Okay. So you need to check that after apply g, the condition hold. Okay. So want to show gy is greater than gx. Right. So what's gx? Gx is s cubed, which is x dot x dot x dot x. Right. So I can replace one of them with y first. Okay. And then I can replace another one with y. right? And then I can do go through them. This is G1. Yeah. Similarly, you can show for the others. So this one a bit tricky, but still the same concept. Uh, so maybe left-handed exercise. Show that V1 and GX. So this one a bit tedious because when you multiply minus the sign will change. So swap few times before you can show the inequalities. Okay. And then I think if I'm not wrong, I include the tutorial. If something is strictly increasing, then it is 1-to-1. If not, it's in the tutorial question. I mean the question behind the textbook after the topic. Okay. And then next. Yeah. Okay, I write down the notes here. So uh, I think tutorial question, or if not, it's in the textbook. So show that any strictly increasing function is 1-to-1. Okay, this one is easier to do. Okay, after you check 1-to-1, next thing, the second property is we want to know if it is onto, because we know that the range is a subset of the codomain, right? So we wonder if we can reach all the codomain. So this property is called onto, or from A to B, it's called onto, or we call a surjection. Okay, if and only for every P in B exists a A such that A equal to B. Okay, then F is also called um, surjective. Okay, so for example, fx equal to s squared, is it onto? Is it onto to the real? Is it onto? Hmm? Is f onto f equal to s squared? Uh-huh. So, is it onto? Can you reach all the number in the real using the function? Yeah. How about a negative one? For example, -1. Can you reach -1 here? Uh, cannot, right? So the square of every number is positive, so you cannot reach negative number. Right? So this is not onto. Okay. But s cube is onto. Okay. So for every number in R, okay, or every number in R, sorry, out my domain. So every number in R, you can take x equal to cube root 1. Okay? At x equal to cube root y, then you will get sent to y, which is 1. Yeah. So for every element in your codomain, you can find a pre-image. and this is onto. Okay, yeah, onto the codomain. Any question or not? No? Any question? 42. Okay, and then next, so if a function is both onto and one-to-one, we call it a bijection. So a function is bijective, okay, or is a bijection, or is a one-to-one correspondent. Okay, it's different from one-to-one. This one is one-to-one correspondence. Okay, if it is both one-to-one and onto. Okay. So for example, we have this running example here. So we have this running example. So f x equal to x squared is not bijective, but gx equal to x cubed is bijective. Okay, this bijective, since you see that this bijective send element to element, so there's one-to-one correspondence between the element, so they actually can see the cardinality of the set. Yeah. So if you have a bijection between two sets, that means the two set has the same cardinality. To link back what you learned last week. Okay. So since you see, since this map is between R, right? So there should exist a bijection between this set. Okay. And S cube is one of the bijection you can find. You can find more bijection between these two sets. Okay. So if you have bijection between two sets, then the two sets will have the same cardinality. So we have this table here to sum up in summary. So one-to-one, so one gets sent to one, okay, not onto because you don't reach this element here, okay. Onto, every element here have a pre-image, okay, but not one-to-one because A and D get sent to the same element, okay. One-to-one and onto, so one-to-one, and every element got a pre-image. Okay. Neither one-to-one and onto, so got two get sent to the same, and one doesn't have a image. Not a function. Yeah, this one is a bit unfortunate because you send A to different places. Yeah. So one number you only get sent once. And then also to show that something is injective, you need to assume that fx equal to fy for any x and y. Of course, if x equal to y, then to satisfy the property of a function, they have to be equal. So assume they are not equal. Not I mean doesn't not assume that they're not equal, but in the end you need to still show that they are equal. Okay. And then not injective, you just need to find two things but get sent to the same thing. Okay. Remember the logic, the negation of implication. Right. Negation of implication. Okay. Surjective, for every element in the codomain, you need to find a pre-image. If it is not surjective, just find that there's one thing in the codomain that's not met by anything in the domain. So since we have the bijection between sets, that means we can go from one to the other. We also can come back. Okay. We also can come back, define the inverse image. So now I will define the inverse image. That's it. Okay. So if we can go from A to B, we also can go from B to A if there's a bijection. So let F be a bijection. Okay, maybe I introduce a notation here. So good notation here. This time I introduced earlier. So if I put like this, it's onto map. If I put like a hook, it's an injective map. So since this is a bijection, so it's a hook plus an inject onto. Okay, so it's a bijection. So in case you forget, I put bijection here. Okay. The inverse function of f is the function. Okay, what's the inverse function? It's a function. So a function is what? An assignment. Okay. So how should we assign this thing then? So we should assign. So we should assign every B we should assign a thing in A. Okay. So given a B, how should you find this A? Okay, you should think. So f is a function that assign to an element B in B. Okay. The unique element in A, point A, such that f A equals to B. Okay. So the inverse of the function we wrote f inverse. Okay. Hence f inverse B is equal to A. So what is this A? This A is what this F tells you on. Okay. So it's the pre-image of this B, right? Because this is bijection, which is onto, we can find an image. Right? Okay. And then actually to be pedantic, you can example, you should show that F inverse is a, a well-defined function. Okay, that means you don't send one thing to different thing. Oh, yeah. Okay, it's not well defined. It's just a function. Just show that it is a function. Okay. Then we call that f is invertible. Invertible. Okay. For example, fx. You see, fx x squared is not bijective, right? So in particular, it's not invertible. Okay. It's not invertible on R. Okay. Because why? Because f minus 2 equals to f2. Right? So if I give you 4, so you should send the 4 to minus 2 or send to 2. You cannot send to both of them. Right? So you cannot define this inverse function. Okay. But gx is invertible. Okay. So you can show that actually G inverse x is cube root x. Okay. So the inverse function is cube root x. Because this is just now how we find the pre-image of every element in the codomain, right? And this is unique because it is one-to-one. So it won't send to two different numbers. So it's defined. So it satisfies the definition of a function. Okay. Yeah. Huh? Any? Okay. 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 Next. Okay, next. Okay, next we can compose two elements. Next. Okay, what time is it? 4:53. Okay, maybe we take a break. 5:03 and then we come back. Yeah. 什么叫给表格？哦，那个，可是这个没有表格对吧？那个只是它的定义嘛。嗯嗯。哦，你讲那个 set 的话，嗯，哦，我的，对，但是这个哦，其实跟这个是一样，注意的，对，它是一样的。我希望我不会出这个了，对，嗯嗯，我觉得我会给这个，我觉得会给上面这个，但是你可以从上面这个领悟出下面那个，因为他们两个有关系。如果给两个就印太多，我觉得也没有用的。但是名字差不远，只差一个名字差别吧，只是这一个的名字差别，其他的是不一样，就这一个名字不一样，其他是一样。嗯，下一节课。
小失误。这里
对对对，哎，我这个改上个没有改过。哦哦，你是说我的那个我放上去的没改，是不？
就是是笔录对。
可以可以可以可以，我只记得要改要改，我只记得我在那个我在班上改了，但是是不是没改到？我看看，等一下我看看，你是说我没改的吗？要改要改，等一下要改，不然等一下，等一下，等一下，我以为我改了，可能我改在另外一个版本。看一下，这个错是吧？这个是对，union 的错的，我记得错。我在教课的，我看到我干嘛这样写？我来讲，这个是什么？少，
就是
少，
这里是从这个地方是不是
这个在哪一课？
是在
在哪里啊？很熟，这 tutorial 问题。嗯，很熟，哪里？这里
是
不是？
标注一下。
要改一下，嗯，哦，这里，OK OK，这里，好，谢谢，啊，没事，你下次提出来就可以了。然后人家也是傻傻的，看一下也是错。
就是
哦，没事，
就直接贴上去。
可以可以可以可以可以，呀，嗯嗯你说了，
是我觉得他这个，
嗯，
他不应该是，就是
是什么？
那个空集是另一个空集的真子集。他我还在网上查了一下，他就讲的是个 empty set 也的那个 proper subject 哎 non-empty set。
对呀，可是我不是问那 MT 我是问 MT 生。
对呀，
对呀，
所以说这个就是错的到，它不是只是 non-empty set 的 proper subject，所以说
没有，OK OK，这个问题问错了，这个是等一下我想一下，我要问，OK 也可以这样子问，但是这个答案是什么？
没有写答案，让我们
对呀，没有答案。
对，然后但是它根据定义
对
就会是存在 X，就是
呀，对对对对对对，
它就套进去了呀，它不
你套套看呢，
这样
所以你得到什么？
说，嗯，会有任意的一
呀
个 X
呀，
属于空集，
对，
同时这个 X 还不属于空集。
没错没错
嗯
没错，
没错，
这是什么东西啊？
这是什么东西呢？
对，这是什么东西啊？对，我就是要你想这是什么东西，这是个什么东西？
这是个错误的和谐，
所以呢，
所以说，
咦，没有这个 set 嘛，
对。
所以就没有这个 proper subject 存在哦。
所以说我证明它是错的。
不是，证明没有呃 empty set 没有 proper subject。对，
我以为是这个，
没有，我问你是什么？它是没有东西。哦，就是R 是一个 set 嘛，R 也是另外一个 set 嘛，那两个 set 是可以存在一起的嘛，
对，
所以就
它没有后面等于那个
什么？
就是它这个写出来
哦，就是说你记得 R square 吗？还是你们没学过？就是那个 graph 嘛，所以你们每次画这个 graph 的时候啊，这其实就是 R square 的，这条是 R 嘛，这条是 R，那你 R 乘 R 乘在一起过后， 你才有这个 R square 出来，所以你有每个这个点啊，这个 xy 啊，xy 点啊，对吧？所以我写不出来，因为这个这么多点，我可以写啦，我就说 R 乘 R 是 xy such that x 在 R 和 y 在 R，这样，这样，我要不要？我不能够 list 出来，但是我可以写出这个嘛，我觉得可以。这个是什么时候啊？这是什么时候啊？我加进去啊。因为这个问题问的很好。对啊，也是会有人看不懂的，所以问一下大家会比较互相学习。在哪里？我这里。嗯嗯，
这个是说的是这种集合的表现形式的
因为它没有符合那个第二个 subset 的条件，就是有一个这里的东西不在这里，它没有，它全部这里的东西都在这里，理解？你这个是最后一题了。OK，我现在解释，因为要开始，我把这样。Okay, yeah. So just now your friend asked me about this definition of R cross R from last week. So R cross R is ordered pairs such that the first coordinate is in R and then the second coordinate is in R. Okay, this one by definition. And then we also have this question here. And then a few typos I fixed already. Later I will upload again. And then about one tutorial question here. Okay, here. So this one is a frequent asked question also. I also got a question from the other class. Oh my, as well I edit here now. Okay, so this question is asking about the proper subset. Um, okay, so this thing is false because, okay, so these two are the same element. So in set, we regard them as one element. Okay, if multi-set is different, but in set, they are the same. And then this question is asking about whether these two are the same set. So whether A is a proper subset of A or not. Okay. Of course, if A is a subset of A, this is true. Okay, but it's not a proper subset because everything in the right hand side is in the left hand side. Okay, so it's not proper. OK 吗？OK 吗？那位同学，我忘记你的名字了，叫你的你，刘星啊，刘星，OK 吗？Make sense 吗？OK，make sense 吗？So yeah, if A is a subset of A, then it's true, but if it is not a proper subset because you can't find an element here such that it's not in the left hand side. Make sense or not? OK 吗，刘星 Okay. So the question is given you a set, whether you have to determine whether it's a set or a multi-set. Okay. So if the question didn't mention multi-set, every time it will be a set. Okay. Only when it is mentioned multi-set. Okay. Yeah. Okay, good. Very good question. Okay, that's a very good question. Okay, next. Uh, so do you all know how to find the inverse of a function, or did you need me to teach you the technique how to find the f inverse? You want recall? Okay. Okay, let's recall. Okay, recall how to find the inverse function. Yeah, so like for example, this function here. So recall how to find the inverse. Recall how to find inverse function. Even how to find even. Okay. So let's say we given this function here, example, and then this is the s cube function. Okay, we want to find the inverse. So first, okay, now when I teach this method, right, try to think of the definition of the function and then the pre-image and the image again, so that this method will make sense to you. So first, let gx equal to y. Okay, so y cube equals to 1. Well, so what does this mean? So I so I need to find the inverse image. So I need to take something. Wait, why I put a cube here? So it's too big. This is too large. Okay, so I need to take an element from the codomain. Okay, and then I want to find the pre-image. Okay, so but G is defined as what? The image looks like what? Y cube. Okay, so your codomain, all of the codomain element in the codomain looks like cube to cube of some element in the domain, right? Make sense or not? So x here is in x here lies in the both of them are R, sorry. So this one is the domain R. Okay. This one is in the codomain R. Okay. So you set gx to be okay. So yeah, okay. I shouldn't. So x will be x will be equal to cube root of 1. Then we will define g inverse y. Okay, or g inverse x equal to x. Okay, so why we set cube root y here? Because we found that this y, okay, we found the pre-image of y, which is hero of Y. So this G inverse is defined as the pre-image. Okay. So this X is the pre-image of Y. Okay, so I should say from okay, I have a remark here. So here is the image of Y under G. Okay, so you define your inverse to be sending your Y to its pre-image. Okay. So yeah, yeah. Confused. And any question to ask? So G inverse is sending the element to it pre-image. Okay, so you need to find the pre-image. So how to find the pre-image? Set your image first, and then find the X. Okay, this is the pre-image of your Y. Okay. Okay. A bit confused again. Got question or not? Question or not? Any question or not? What's this? Okay. Okay, but okay. There's one way to check whether your pre-image, the inverse you find is correct or not. So there's one way to check. Okay. So to check that, we need to define a composition of functions. So let F be a map from A to B, and G is a B to C. Okay. Then the composition of function F and G. Okay. Uh, denoted to factors. Okay. Is the function from A to C defined for every A in A, and G A equals to F G A. Okay, so this is the function. Okay, you might think that this two is like similar, but it's actually not, because this is actually like you do G on A first. Okay, so after you do G on A, then it become an element in. Hey, did I write something wrong? Okay, I write something wrong. So we should start from F, right? Because F takes element from A. Okay, so we take A, and then we take F add on A, and then this one will go to B, right? Okay, so I should write A is in A, and then after A, A will get sent by F to B, okay? And then we apply G again. And then G will send things in B to, I use the different color to denote the bracket, okay? So F send things in A to B, okay? And then G send B to C, okay? So one way to check your inverse is correct or not, so there's a theorem. Okay. The bijection left A, B projection, and then A and B offset. Okay. Then if you compose one way, it will be identity, and you compose the other way is also an identity. Okay. So identity ID is a function, is the identity function, the function that sends element to itself. Yeah. So for example, just now we say that f g and g inverse x, right? So what do we have? So we have x cube, right? And then g on this thing is 0x cube, which is x. So you send x to itself. Okay. So you also need to do the other way around. So what do you have? You have g inverse on x cube, right? And then you do cube root on x cube, which is which is x again. Okay. So both way you send the element to itself and x to x. Okay. Okay. Next. So next we will define the graph of f. So the graph of f, okay, denoted by um do I want to denote? Maybe no need. Just define is the ordered pair A B, okay, such that A in A and B in B. B in B and FA equals to B. Okay. So for example, just now, if we just restrict our domain and codomain to Z for x to x squared, okay. So Z square is actually a lattice. So Z square is a lattice. So this thing live in the A cross B, right? So Z square is a lattice. So the lattice is like this. Extend infinitely. So let's say here is the 1, 0, 0 point, and then we'll go 1, 0 here, 0, 1, 1, 0, and then 0, 1 here. Okay, and then we can extend this graph here. So which point is in the graph of f? This is, okay. So 0, 0 is in here. Okay. So 1, 1. Okay, 1, 1. And then minus 1, 1. And then what else? 2, 4. And then minus 2, 4. And then you can plot this graph here. Okay. So this is Z. cross Z. If you want to look at R to R, then this whole thing will become the continuous, right? Okay, so the whole thing will become continuous. You need to include every point, and then you will get something like this. Okay. So let me, yeah, okay. Okay. Okay, so this is the graph. So graph is what? Graph is an ordered pair. Next. So next, there are two important functions maybe you want to learn. So one is called the flow function. Flow function. Okay, which is denoted by this. So flow function KR to Z. Okay. So you take a number to where? Then real number x to the largest integer that is less than or equal to x. Okay. And also we introduce the ceiling function. The ceiling function sends a real number x to the smallest integer, to extra integer that is less than or greater or equal to greater or equal to x. Okay. So for example, the floor function says 6.52 where 6, 7.252, 7. Okay. And then the ceiling function sends 6.62 where 7. And then 7.252, 8. Okay. Yep, that's right. Okay. So these floor and ceiling function also satisfy some nice property, such as this scalar. You can bring the minus up, and then if you add some scalar, you can just bring the scalar up. You can show it, but not important. But maybe it's good for your coding stuff later. Okay, next, we will end this topic with the matrix. So the matrix we learned here is quite elementary. Okay. So in this course, a lot of this material is just study the structure, but not deeply into the subject. Okay. So what is a matrix? So a matrix is rectangular arrays of numbers. So usually it's a m by n matrix. So we call it with m rows and n column. Okay. It's an m by n matrix. Okay, so it's something like this. So you got some number here. Okay. And so on. So here is m, here is n. Okay. M rows and columns. Okay. And then when if m equals to n, then uh, uh, then the n by n, if I put it, the matrix is good. Okay, maybe phrase it better. So the matrix is square if it is n by n matrix. Yeah. So the what's that called? Length and width thing. So the number of rows and columns are the same. And okay, so some notation here. So usually we will label the entries here. So the entries like A11, yeah, A12, A13, until A1n. Yes. So the first one will denote the row, and then second will denote the column. Okay. And then A21, A22, okay. And then here going down A31, A41, and then dot. And then when you reach the bottom is AM1. And then diagonal, you will notice is like repeating pattern here. Okay, so this feature is very important for you to define which terms in your matrix. Okay, because in your coding, maybe you need to consider different dimension, n-dimensional what data. So you need to make sure how you deal with this entry properly. And then the ith row. So when we say the ith row, so the ith row, so the ith row is going this way. Okay, let me just draw it first before I. For the okay, so for example, this one is the second row. Okay. So the ith row of A is the n by 1 by n matrix. Okay. AI1, AI2 up to AIN. And then the I column of A is the n by 1 matrix. So it's the standing one. It's a m, sorry, m by n. So it's like the A1J, A2. Wait, what am I doing? So, yeah, correct. So I, right? So it's the I, 2I, 3I until AMI. Okay. And then sometimes you will call it the IJ element. Okay, so the IJ element of A is AIJ. Okay, so compactly, we don't write the whole thing up. We just write A equals to AIJ. Okay, so maybe we'll mention that I is going from 1 to n. I is going to I to m. And then j is going from 1 to n. Okay, we want to mention where the range of I and j is. Yeah. Okay, next. So to talk about this, then we can also introduce two kind of operation to matrix. So one, we can add them together. So, but we can only add them together when they have the same size. If they are the different size, we cannot add them because there are ambiguity on adding them. Okay. So A and B will be defined as adding the term entry-wise. Okay, entry-wise. I think you should know how to add them. Do you know? Have you learned this before? So unravel this the definition is when their ij is the same, you can add them. So I 1 1 can only add with 1 1. Okay. 1 2 can only add with 1 2. 2 1 can only add with 2 1, and then 2 2 can only add with 2. So what's this matrix here? Huh? What's the matrix here? What is A11? 7, 8, 9, and 2. Okay. Okay. Good. Okay, I think this one is easy for you. Hmm. And then next, how about multiplication? So multiplication, they cannot have the same size. But what size they should have? So let A be and B such that A is n by n maybe. Okay. Matrix and B is n by P matrix. Okay. Then A dot B is m by P matrix. I think I'm not wrong here. Okay. Okay. Such that what? Such that when A dot B is Cij, when such that if then how to compute Cij? You take the row times the column. So is Cij is the row times the column. Wait, row times column. Row vector times the column vectors. Okay. So this one is row, right? Row vector times the column vector. Okay. So notice that when you multiply, right, the middle one they agree. So this is the features of the multiplication of matrix. Okay. So to give you this, okay. So I should write out something so you are aware of. So n times n t. Okay. So you get m. Okay. N by n and n by n, n by p, and then you get. Okay. So where's my picture here? Okay. So this is the picture here. So you take the row and the column. Get the row, the column, get the row, and column, row, and column. Okay. So you see that then the middle here will agree with the middle here. Okay. Not middle, I mean the last entry here will agree with the starting entry. Yes. Similarly here. Yeah. Okay. So you see when they apply together, right? The start one is 1, the end one is 1. Okay. So they become the new C11. Okay. So similarly, if you multiply here with here, so the starting is 1, okay, the ending is 2. So this is your new C1. Okay. Yeah. Yeah. Okay, for example, let me show you this to really click into your mind. What's this matrix here? So this is actually the 3 by 2 matrix. Okay, 3 by 2 matrix. This is 2 by 1 matrix. So what do you get? What size of matrix do you get? 3 by 1. Okay. So what's the first entry? 8. Second entry? 6. Third entry? 29. Yes. Okay. So 3 by 2, 2 by 1, you get 3 by 1. Okay. Next. Okay, next we introduce the just now we got identity function, right? Now we also introduce identity matrix. The identity matrix, okay, of order n is the n by n matrix. Okay, so In. So I write this compact notation here. What's this delta ij? So delta ij means it is 1 if I equal to j. It is 0 when I equal not equal to j. So just now I told you that when is it I and j is equal in the entry? Yeah, it's on the diagonal. So this identity is the one on the diagonal entry. Okay, I put 0 there. Okay. So for example, like uh I2 is 1100. Okay, and then going on. So next. So just now we mentioned that a function is invertible, right? So a matrix also can be invertible, okay? So how is a matrix invertible? So it is called invertible if there exists another matrix A inverse such that A inverse equals to identity and A inverse equals to A. Okay. Then the matrix A inverse is called B inverse of N. Okay, so up to now. So you can see matrix and function actually share a lot of similar properties. Okay. But not every function can be represented by a matrix. Okay. This is not covered in your note, but this one is very very fundamental that uh if your function okay, if your function is between two uh, there are some functions that can be represented by matrix, and then this kind of functions people love to study because they can turn this question into matrices, and matrices are linear algebra. So linear algebra has developed a lot, right? And maybe you also didn't touch about linear algebra. Is your course content linear algebra? Is your course like the degree? No, just calculus? Huh? Not even calculus. Or DMT don't do calculus. Because I know SWE got. Oh, okay. Okay. I'm not sure why you do discrete. Okay, okay, never mind. Okay, because another computer science they do calculus and linear. Okay, never mind. Okay. Okay, next. Uh, so if we have a n by n matrix, we can consider the transpose. So what's the transpose of A? Is you interchange the rows and column. So you become a n by n matrix. Interchanging, interchanging rows and columns. So if AT written as this Bij form, then Bij equals to AJI. Okay. So I think this one is clear if we look at one example. So for example, look at 2, 3, 1, 1, 2, 3. Okay, so this is our A. So the A transpose is you turn this row become a column, okay, and then you turn this row become column, where you get 2, 3, 1, and 1, 2, 3. Okay, so this is the transpose. And then there's some nice property called by a particular set of matrix if the matrix is equal to its transpose. Okay, if A equals to AT, then the square matrix A is called symmetric. Okay, so for example the identity matrix is uh, symmetric. Hey, you guys haven't learned eigenvalues? No, never learned. Never learned. So these symmetric function have a lot of nice property. Yeah. Maybe soon after next you will learn. Not sure. Okay, so if it is symmetric, then it is symmetry along this diagonal. 1, 2, 4, 2, 1, 3, 4, 3. Okay, so we call this kind of uh, matrix symmetric. Okay, and then we also can just study matrix that have only 0 and 1 inside it, and then we can do the Boolean, the n and all using the matrix. Okay. So in this, we can do a lot of computation at one go using matrix. So let's see. So these matrix are called a 0, 1 matrix. So let's consider a matrix such that uh, either 0 or 1. Okay. And then remember that we have remember the Boolean arithmetic? So last time we mentioned that they satisfy identity that belongs to Boolean algebra, right? So remember the n. So if you take n, it is 1 if both of them are true, right? If false, and then this one otherwise, only otherwise. So how about or? Okay. So this is true only if, okay, this one a lot. If b1 equals to b1 is true or b1 is also b2 is true, and then otherwise. Okay. So in this case, you also can define the uh, so let A and B. So let A and B be the 0, 1 matrix. Okay, be a 0, 1 matrix. So we can define the join of A and B. And we define the join of A and B. What's the join? So the join is denoted by A or B. Okay. So A or B. So A or B. So the entry is defined by uh, A, A I or B I J. Okay. So you replace the plus, become this or. Okay. This or in this Boolean arithmetic. And then the next one, you will suspect I define this join here. Okay. Is A and B. Okay. So where you have to take n for all the individual terms. Okay. Right. So for example, so click into your mind. So A, so like this. So let's take the join. Hey, this one join or mid? This is mid. Sorry, this is mid. So mid have to intersect. So what is this? 1 and 0 is 0. 1, 1 is 0, 1 is 0. 1, 0, 0. And then the other is mid. Sorry, join. Okay, 0, 1 or 0, 1, 1 or 1, 0 or 1, 1 or 0, 1. Okay, yeah. Okay, so the last thing, yeah, the last. So last year is a Boolean product. So what's the Boolean product? Maybe I don't repeat the condition. You should know what's the condition of A. So the Boolean product of A and B. Okay, we write A dot B. Okay, if I write the entry like this, where you just replace the n with the this one, you replace the multiplication with the or. Happens. You replace the multiplication with the n. Okay, and then you replace the plus with the or. So this is similar to what we did for the matrix, but replaced with the two different operation. Okay. So this one, okay. So this one is for example, this is m by n. This is matrix. This is n by p matrix. So this is a m by p matrix. Similar to the what we do for normal matrix. So what do you get for this? So you get 1 times 1, 1 and 1, or 1 and 0. Okay. 0 and 1, or 1 and 0. 1 and 0, or 1 and 1. And 0 and 0, or 1. Which is you get 1, 1, 0, 1. Is it correct? Check my answer. So why we want to organize this Boolean number into a matrix? Because sometimes you have different dimension. So this matrix, right? So this matrix actually add on the space. So that means this is a function. The matrix, one matrix itself is actually a function from um, if it is an n by n matrix, okay, it is a function from Rn to Rm. So in this case, it's R2 to R2. Okay. So you that means you give me a vector. I apply this matrix, I give back you another vector here. Okay. So that's why we introduce matrix. Yeah. And then after the function. Actually, there's some deep connection between these two. But there's no time for this course. So we just introduce the basic definition here. So if you want to do a lot of computation at one go, so you need to arrange them into matrix first. And then you can just go through this matrix without checking what they did on the space. Okay, on the set. Okay, so this is why we care about matrix. And then we talk about function. Yeah. So matrix can compactly deal with a lot of functions, a few functions together. Any question or not? Okay, if not, take a rest and then think about some question and then we come back for tutorial. 6:05.嗯，这个是真子技术。什么是真子技术？不要，
就是它不是它的别人，它不包含它本身和空局的。就是这样。
所以wait, let me see.
它的符号，所以是这里要写一个撇，还是上面这个？
对，两个都一样。
两个都一样的是吗？
对。这个OK，我写出有这个也有这个嘛，然后这一个和这一个和这一个都是一样的。
哦。然后多重集的秘籍是什么？就是
什么是秘籍呀？多重集是 multi-set
power set
的 power set
power set
的 multi-set 的 power set 是什么？multi-set 的 power set 是什么？multi-set 的 power set，我觉得看看，我觉得有错，我没有 define 对不对？我觉得是可以直接从之前那个 define 上，但是我应该是，我觉得应该就是有一个啊，对不对？加上2条。我觉得就是普通的那个，就是 all the subset of multi-set。OK， 我知道了。
就是
因为
很多个元素，就是重复的元素。 不是有。那我在
什么意思？比如说这个嘛
对，
，OK，加一个2比较好。
嗯，
所以这一个应该是它的 subset，所以它的 power 应该有这个，
哇塞，它会有这种，
会有这个东西。然后这个也是它的 power，这个也是它的 power，这个也是 power。
哦，它的 power set 也是一个，
但是
也会有多重组，对吗？
你说
你是这也是多重组，
你说这两个同不同？是吧？这两个它同吗？可不可以同？你是说可能这个1是从这个来，这个1是从这个来？
对，
我也觉得好问题。是我要符合什么？
这个顺序是怎么看？怎么写？就是这4个顺序是怎么写？然后这是0在这里，10在这里。
哦，
再点4。
这一行，
我就横的还是竖的？
对，全部都横竖。
这边是横的，这边是竖的，左边横。
不是这么说，因为这一个的数是从第一个数来，第二个从第二个数来，对呀。说第一个是从第一个横的第一个数来，第二个是第一个横的第二个数来，然后第
3个是第二
个
个
横的第一个数来。
谢谢啊。
有道理，有没有这样的东西呢？不要讲错东西，我这说明它总共是有3行产品，对吧？就有一个 BC，看在下面讲的。BC，
所以不重复它的多重组，
对，你觉得有问题吗？这样子？
怪怪的。
为什么？为什么？
确实怪怪的，
怪怪的，感觉没有跟什么东西有矛盾吗？
它是没有，
啊，
好像没有。
没有和什么东西有冲突的。
它会不会就弄个这样的话？
呀，
那这样还能够说，如果一个集合的多重组，它的相等。
我觉得这个好问题。好，等下，power set，好，对咯，这样的话就应该是这样了。如果这样的话，它就是一样了。如果我们这样子讲，它们就是一样的，但是有问题，应该没问题。
我也不知道有没有问题，就感觉可能这个不行。
好像是一样的。对，如果这样讲的话，他们好像是一样的。
它会有一个这样的集合式，
来，
它会有一个这样的。
哦，对，所以它也不太一样。
那有没有可能会有？
不可能，不可能。让吧。OK，嗯，
那好像是。
OK，
然后还想问一下，说 x3次方是个递增，然后我觉得那个证明对，但是你那个在主菜里那个位置它不是平的，在那个点上，它左边右边是不是相对？
谁跟你说那个点是平的？谁告诉你
它的导数是零啊？
它的导数是零？
啊，
没有，导数是零有三个情况，
有三个情况。
一个情况是它是 maximum point 或者 minimum point，或者它是一个它是一个转变的点。
它就是这样。
对，但是
它的导数是零，是不是说明它那个点的趋势就是平？就它前后
趋势
会是一样的。
等一下我看看，那个好像有三个情况。不好意思，那个线你可以放，你要放这里。线，你说导数是零，是不是？
嗯，
然后它周围是零啊，好像不是这样解释哎，但是我想一下，讲跟你解释。Stationary point，哎，你看这个也是零，OK，可是我刚才讲解，
啊，这个导数是零。
the stationary point，不对，inflection point，
对，就是这样的。它为
curvature
什么说它是
change，好像这个点的时候它也是零哎，f prime 是 f prime prime，
导数是零，就是 x
呀，with an x，所以它导数是零。哦，它是 f prime prime 等于零，可是它没有解释 f prime 零，导数是零 imply 它是什么？If f prime is 0, then the point is stationary point of inflection. If f is not an inflection, it's a stationary point of inflection. 什么意思？inflection point 的意思是说它的左边和右边，一个是加，一个是减。它的 f prime prime 应该
就是它的导数的左边是一个加一个减。
对，就
导数的
应该是 f prime prime 是加减还是 f prime 是加？f prime prime 还是 f prime？f prime prime
导数的导数，
对，导数的导数。
它的导数应该是等于哪些？
这听不懂，这是什么？啊，你说不懂怎么乘啊？不懂怎么乘啊？啊，OK，那这里有没有乘给你看？比如说我们看它为什么是14啊，就是它拿第一行乘它的值，第一个 row 乘第一个 column，所以1乘2拿到3，哎，不是1乘2，注意啊，1乘2拿到2，然后0乘1等于4乘1等于12，12加2等于14哦。然后你这个圈起来干嘛？你是说这个等于什么？所以比如说你拿第三行乘第一行，你得到3乘2等于6，1乘1等于1，0乘3等于0，所以6加1等于7，所以第三行的第一个是7。
这边的这些，这些
呀，这一些是从这个第二个 column 出来的咯，所以你拿第一行乘第二个值的，你就会拿到第二个位置第一个号码，所以1乘4是4000，所以4哦， 4。OK， 然后第二个呢是从第二行乘第二个值的，拿到这里428，8加1 9， 1乘0 0，这里是9，可以吗？然后试一下吗？再试一下找结果，可以吗 ？OK， 啊，如果我太快，你下次把我暂停下来，我再重复一次这个。对，
这应该是很美。
Yeah, you can try a tutorial question and then we will discuss at about 6:30. Yeah, 6:30. So,
是这样的，它的两次导数是这样的。
两次导数是这样的意思是说，因为两次导数它这里是加嘛，这里是减嘛，对，所以它如果这个点，它就在这个点的时候，它就从减变加或者从加变减。
这个负号是正。
耶，这个是这个 inflection 的意思啊，但是问题是，
就是我的意思，
为什么导数1是0呢？
就是我的意思，
呀，
导数是0的话，是不是就因为它左右两边离它最近的那个时速就是应该是一样的？
不是，
如果不一样，那它不应该是有正的。
但是问题是一个是凹上，一个凹下，它又不是。
什么叫？
给我想想，我怎么跟你讲啊？因为它，因为 OK， 因为你说那个导数是它的那个 gradient 嘛，对，它斜率。但是问题是你一边是斜这边，一边斜这边。就比如说，
就是
你看啊，
斜率，
比如说，这一个比较明显，这个是因为这边是这样，这边是这样嘛，对不对？
这是一阶导。
对，但是这个的情况跟这个差不多是。
我其实就是想知道那个，
你说，
就是它导数等于0，
对，
是不是就意味着它在这个点没有增长的趋势？那它下面一个点应该跟这个点的值应该是要是一样的。
不是，
那如果不一样，它不应该就增长？导数的不是最开始定义是什么？加一个 delta x，
没有错，
那个除以那个什么？
没有错，
啊，
没有错。但问题是，但是你看啊，那个导不是它可以导左边或导右边嘛，对不对？
走左边，我就
所以
导右边。
你
那比如，我就当它导右边了。
不能，
能，
因为你是取那个 limit 嘛，所以你是取那个叫什么？取 limit， 你懂 limit 吗？
limit 是什么？
那个LIM 嘛，这个是什么？
都比的极限
啊，极限里面，所以你取 limit 左边过来，
就是左边
跟右边过来，
负0和正0。
对，它要遇到嘛，因为它是 continuous 嘛，你都画出来了，它是 continuous， 因为它要遇到嘛，所以一边是加，一边是减，对吗？那你越来越近，一个加一个减怎么能够equal呢？只能够当它们是0的时候，
所以就在0。
可以明白吗？
可以，但我觉得没有回答我刚才那个
什么问题？
就是它是0，为什么不能带0？
不带什么？
它后面跟这个值，
后面跟它
你就单纯想那个，就不一定要这个函数，像实在是只要它有一个这样的一个点，它的导数为0，那是不是就应该说明就是它跟它后面的点，它导数的最基本定义是
没有，导数的定义其实是一个极限的定义来的。
是这样的一个什么东西？
对，但是这个是一个极限来的。
对，
它不是说它存在一个点让它就是它这个0等于0的这个东西，不是它不是你放一个 S0进去，它有这个东西，它是一个极限来的，它是永远非0， 然后非零非零非零非零非零非零非零，越来越靠近，有没有？因为
那他怎么能够在一个点就取到呢？
没有
他最后是取到的，在那个
对，在那个点的时候，但是问题是这个斜率你一定要有2个点，
一定要有2个点，
对吗
那就是
？gradient 一定要有2个点嘛？
那一个点就是我取的 x，然后再一个点就是 f(x) 这样，就这2个点，然后它的斜率为等，那不就这2个点的直线？
写一下，你看我写一下，这样写一下。OK，所以这个 S0是你要学习你要看的那个点嘛，对不对？但是你是看它附近 x 的点嘛，对不对？但是你是取它越来越近、越来越近、越来越近嘛，对不对？这个率，
对，
就是对吗？对吗？是这样讲吗？对吗 ？OK，
对，
很简单的就是这个东西，比如说你要拿这里的 gradient，第一个你会拿跟这个的点的斜率，然后第二个你会拿这个点跟这个点的斜率，然后慢慢，对不对？
对。
但是问题是在这个点当下的这个点，不是？
在这个点，
它怎么定义？不是？它是用极限来定义的，
就是无限接近这个点的另一个点。
没有啊，就是那个点啊，没有说无限接近它又是，
所以就是它本身。那这样每个点的斜率
OK，这个是极限的奇妙之处，就是你要你要你要，因为你知道你不能够直接算它，但是你就越来越近，越来越近。但是这越来越近，它又给出你一个答案，
它怎么给？
但是它怎么给，对不对？它又不是透过另外一个点给你的哦，
它就是我那个点。
它就是你那个点，你定义为那个出来的那个极限是你要的东西。
所以说，就是如果那个点的斜率为0，就是这个东西为0，但这个东西为0的时候，这个点和这个点其实就是一个点，是这个理解吗？
不是这样子，我跟你说，所以我跟你说，所以如果你再想回，OK，我跟你说，它的情况是这样，所以再这样想回这个然后你要看这个的导数在这个点嘛，但是这个导数是用极限的定义来做嘛，那极限的定义是什么？你就是那这样子，然后越来越近嘛，对不对？然后它的这个每一个号码它是趋近于0，但是没有到0，有没有？所以可能第一条你拿到0.5，第二条你拿到0.25，第三条你拿到0.1、0.01、0.001、0.001，所以你越靠近你就越靠近1一点，所以这个整个那个
就我越
极
靠近那
限，
个点，我的答案就越接近1。
对，然后这个极限是0，所以我们把这个导数定为是0，有没有？你没有怪怪，你可能不理解那个那个极限的定义，就是比如说这个是第一个点，这是第二个点，这个是第三个点，这个是第四个点，所以我们是从啊、看所有的点越靠近这一个点哦，所以 x1、x2、x3、x4等等，一直跑，越来越靠近这个点。然后你这整个 limit 我叫它 a 了，刚才你写的那个很复杂的东西。第一个它是得到这个 a1、a2、a3、a4、a5，然后这个 limit 的意思是说，我取这一个的。
就是不断往下取，然后就最后取到是0，
取到是0，对，没有人遇到那个0，但是它的极限是0，
他没有说真的有一个0，
他没有真的说有一个点让他得到那个0，但是它的极限是0，你明白吗？所以我们看的是这个号码，你明白吗？
好像有点懂
啊，
所以说它存在所以之前说是求导存在左右，它的左边过来就会是
减0.5，减0.2，减，然后越来越，
然后这个是
然后因为如果你要他们 continuous 连续的话，就这个是在微积分里面。 个有点兴趣，你应该要转数学，应该要转数学。 Okay, let's see. We have okay, so 2.2.32. There's the question asks if A union B and C union B if if B union B then A equals C. Okay, so the answer is no. You can consider this example here. And next one is you change the union to intersection. Okay, such that they're equal. Should the set AC be equal? No. You also can take integer and the rational. And then the next one, they have more condition. I think they have what they have. They have the intersection is the same and the union is the same. So if their union is the same and the intersection is the same, then they have to be equal. The A and B. Or A and C in this case. Okay. I just keep going. If you have question, you just ask. Just feel free to stop me. I just keep going. Otherwise, there's no time. You just stop me if you want to stop me. Okay. And then for this question, you just use the theorem we did in the class and then apply multiple times. Okay. By seeing that a union is another set, so you can apply because in the class we only mentioned about A union B is A plus B minus A intercept B. Okay. So if you take A union B as one set, then you can apply this formula. Okay, and then you keep applying the formula. Okay, and then you get the result you want. And then next, check whether it's a function or not. So first one, it defines plus minus n. So I don't know I want to take plus or I don't know what to take minus, so it's not a function. Second, yes. Okay. Third, almost a function, but not defined on 0. So unless you set a condition that n cannot be 2 or minus 2, then it will be a function. If you take away 2 and minus 2 from the domain, then it is a function. Okay? Because 1 over infinity or 1 over 0 is undefined. And then 2.3.8, just checking whether you know the definition of floor or ceiling or not. Okay. And then the next one, to check whether it's one-to-one or onto. Okay. So if you send different objects, element to different places, it's one-to-one. If you can reach all the element in the core domain, is onto like this case is not onto, you see, you repeat already. So you have a 4 to 4 element, but you repeat, so you can be onto. And then it's not 1-to-1 because you got two different elements get sent to the same element. So to see whether a function is 1-to-1 or onto is one thing you need to take away from this class. Okay. Similarly, D, you can check that it's not 1-to-1 and not onto. 2.3.22. Okay, you want to show that this function is a bijection. This means you need to show that it is both 1-to-1 and onto. So you want to show that it's 1-to-1, you suppose that it is equal, and then you prove that x and y are equal. Okay, definition. Subjective. So given any element y here, you want to find the pre-image. Okay, so you set your function to be equal to 1 and then find the x. And then I suppose I suggest to take this as an x. Okay, and then I show that if I apply f on the pre-match, then I'll get the y I started with. Okay. So for every y, I found a pre-match. And then B, not bijective because it's not 1-to-1 and also not onto. Yeah, not 1-to-1 should be clear from here. Not onto also you can find a point such that it doesn't map to it. Because this, you realize that this is what? This is some shift of x squared. So you take the x squared, right? X squared is like this. And then you take the minus, so it flips down. Okay. And then 3 meaning the gradient increase. Okay, become greater. And then plus 7, the whole thing shift up. 7. Okay. And then C this function is hard to interpret, so I make it into some elementary matrix. So it's 1 over x plus on the y coordinate. Okay. So if I sketch this graph, is the 1 over x graph. Okay, 1 over x. So x is like this, 1 over x split. Okay. And then minus 1 over x, so turn around. Okay. And then 1 over x plus 2, so shift on the y x value. And then plus 1 to all the numbers, so everything go up. Okay. So it's not onto because I can find one point such that it can't be mapped to some, for example 1. Okay. So if I want to find this function equals to 1, found a contradiction that 1 equals to 0. Okay. Contradiction. So I cannot find this point here. Okay. Okay, next. So this one, D, show that it is 1-to-1 and 2. Okay. It is 1-to-1. On 2 should be easy. You just set it to y and then you find what is x. So I think x is just y minus 1 fifth root. But 1-to-1, like what I said, is hard. So one technique is to use that. This is a strictly increasing function. Show that this is a strictly increasing function. Okay. So f is strictly increasing. 2.3.34. If the composition is onto, then the outside function, the last one should be onto. Okay. So this one is to check whether you know the definition of onto or not. Okay. So if F is onto, suppose you want to show that F is onto, then you need to take an element here, so that there's a pre-image get mapped to the Y. Okay. So what I did is I take one Y here. Okay. I need to find an element B here. But I know that the composite is onto. I can find an element in A such that FGX is 1. Then I just take my GX to be the pre-image of Y in B. Okay. Because G map X to B. Okay. The whole idea is easy, but you need to get around with the logic and definition. The next is if F compose G is 1 to 1, then the function inside have to be 1 to 1. Okay, so I start with what I have, or what I assume, and then I need to show that S is equal to 1. Okay, and then by using the composite is equal. Okay. Next is getting more. So assume that F compose G is bijection, and then G is onto if and only if F is 1 to 1. So two directions need to show. I need to show G is onto imply F is 1 to 1, and then F is 1 to 1 implies G is onto. So I put the two solution here. Okay, just now I think I go a bit fast in the introducing this matrix multiplication, because I thought you guys already learned this before, either in foundation or before uni. But anyway, I repeat once again here. So if you want to, okay, add, I think add is easy, but add because it's just element entry wise adding. But multiplication is a bit difficult, not difficult, a bit more work. So to get the first entry, you take the first row, okay, you multiply the first column here. So for example, 1 times 0, you get 1. So 0 times, you get 0, and then 1 times minus 1, you get minus 1. Okay. And then to get the second one, the first row, second column is to take the first row times the second column. Okay. And then first row times the third column would get the first row, third column. Okay. And then if you take the second one times the first one, you get 2, 1. Okay. 2, 2. Okay. 2, 3. 2, 3. And then 3, 1 here. 3, 2 here. 3, 3 here. Okay. So make sure they have the same length, so you can multiply together. That's why we have these m times n times e like this. Okay. So make sure they have the same length. But these two must agree so that you can multiply them together. Okay. This is the reason why they have to be the same. Okay. And then this one multiplication. Okay. Okay, the next one is I think this one you need to do, although it's a odd question. Although I don't tell you how to find it, but you should know that a 2 by 2 matrix inverse, the inverse of a 2 by 2 matrix is 1 over AD minus BC, and then you swap A and D, and then take negative on B and negative on C. This one you should remember. This is very useful, not for this class, but a lot of other things you want to do. So this question is just asking you to show this, okay, show that it's an inverse or satisfy this condition here. So you just do the multiplication, okay? First row, first column, first row, second column, first row, second row, first column, second row, second column. And then you see that it's the identity function. The next one, why I ask you to do, because this question has some induction, can use inductive proof by induction. Okay. So that's why I added this question in. But one step here, I think they did in before in the question before. If not, it is not hard to prove that if A, B, and also A are invertible, then the inverse of AB is B inverse times A inverse. So swap the order and then take the inverse. Okay. So to check this, if you're really desperate, don't know how to check this, this is just to check that AB times B inverse A inverse equals to identity equals to B inverse times A inverse AB. Okay. This is equivalent to checking this. Okay. Like how you check the 2 by 2 matrix is inverse to each other. Okay. Okay, next one. So this one 2.6.26 is some property on join. Oh, I didn't finish this. Someone finish or not? This one is 1 and 0, 0, 0, 1, 1, 1, 4, 1, it's 1. And then 1, 1, 1, also 1. And then 0, 1, 1 of 0, so it's 1 also. So 0, 0 and 0, 0, 0, 0, right? 0 and 1, 0, 1 and 0, 0, 0, 0, 0. Okay. Yep. Yeah, I think that's it. So in the exam, right? So exam, because I have some proof question, theory question, also computation question, right? So I already look at your syllabus. So I think in the midterm, we will have about all computation question will have at most 30%. Okay, this one is computation. So other is like theory or applied theory question. Okay. For midterm. So you need to more computation is happening on chapter 2 and 3. So this computation you need to learn. So most computation question mostly in chapter or topic 1, topic 2 and 3. Okay. So like find the cardinality and then do this matrix stuff, and then next week we'll have a lot of computation. So modular arithmetic, and then what else? Yeah. Okay. So yeah. Okay, midterm is week 8. Week 8. Yeah. Quiz 2 is week 6. Okay.它是不是一个 function？
对，一个
所以一个 function 就是说，
它是 from z to r 什么意思？从整数变成实数。
对，
是的。但是第二个函数它原本就不是整数啊，它就不能表示整数。因为整数里面不是有零，它这个不能是零，因为 n 方
一它不等于
，n 方不能等于负1，因为它不是 z， 它没有说 n 的范围。
听不懂这个，
就是它这个 z 到 r 什么意思？
就是 n 是减1、0、1、2、3、4、减2、减3、减4，就是 n 可以取的值是在 integer 里。
啊，对，那它 n 方不是不能等于负1？
那又怎么样？
他是想让为什么要 z 到？他怎么样才能 z 到
？1到 r 不一定是你所有的 r 都要有东西被，它不一定是 onto， 它不一定是。
这道题是想让我们干什么？就判断这个函数是怎么，
判断它是不是一个函数。 判断它是不是一个函数？
那这肯定是函数。
哪一个？
这个
第二个？
第二个是
对啊，
函数。
第二个是函数啊。
那第三个为什么不是？
第三个为什么不函数？因为如果 n 等于2的话，你们想到
不能。
啊？
哦，不能。